Good morning. Welcome to the first session of this morning. My name is Xuan Hongtong from Taiwan University. And this morning we have two speakers talking about the two-dimensional materials. So the first speaker is Professor Thygesen from Technical University of Denmark. So let's welcome Professor Thygesen, please.
Thank you. So first, let me thank the organizers for the invitation. I'm very happy to be here. Unfortunately, I only had the possibility of staying for 3 days. I would have loved to stay longer, but so I guess I have to come back another time to see the beautiful country a bit more. So I'll be talking about electronic excitations in two-dimensional materials and van der Waals heterostructures. And but before starting, I would like to quote, just as a curiosity, a guy that I'm sure all of you know. This is Richard Feynman, and when he gave his famous talk in '59, Plenty of Room at the Bottom, he said, among other things, among other visionary things, he said, what could we do with layered structures if we had just the right layers? What would the properties of materials be if we could really design them atom by atom? So this was one of the very visionary ideas that Feynman had already at that early stage. I think today we can surely tell him what we would do if we were able to arrange the layers of materials atom by atom. So we would be able to make, for example, multi-junction solar cells with efficiency that significantly exceeds the Shockley-Queisser limit. Here's an example by putting together 3 semiconductors with staggered band alignment and different band gaps. One can reach, theoretically, power conversion efficiencies reaching 70%. And there are already examples of van der Waals heterostructures where this is from Guang's group in Manchester. They've stacked 20 different, not 20 different, but 20 layers of graphene hexagonal boron nitride and transition metal dichlorogenides. Okay, so I think this is a really fascinating area that we are part of, and that we can soon, I think, really start to design materials atom by atom or layer by layer. So here's another example from the recent literature. This is an example of a wafer scale van der Waals heterostructure. This is a multi-layer consisting of alternating monolayers of tungsten diselenide and molybdenum diselenide. And this is 1 centimeter by 1 centimeter in area. So this is really wafer scale van der Waals heterostructures. Here's another example of a tri-layer. I'll come back to that towards the end of the talk when I'll be discussing excitons in these van der Waals heterostructures. So this is really exciting. I think one thing that is really important is that you can see these layers. They have atomically well-defined interfaces. So it means at the interfaces we do not have the problem of diffusion of atoms that we typically have in conventionally grown semiconductors because of the van der Waals interaction. It's so weak that we get these atomically well-defined interfaces. Another advantage of the weak van der Waals interaction is that we can stack any types of two-dimensional materials, whereas conventionally we are limited to lattice match structures. So we need, with conventional methods, we need to grow materials that have almost the same in-plane lattice constant. So this means that chemistry dictates a lot of what we can do with conventional methods, whereas here it's basically a combinatorial problem. You can stack any 2 types of two-dimensional materials. So we can ask ourselves, how many possible van der Waals heterostructures are there? So if we imagine that we have at our disposal 10 different two-dimensional materials, so how many heterostructures can we make that has 10 layers? So that's 10 to the 10. That's a huge number of heterostructures that we can make just with 10 different two-dimensional materials. In reality, we heard from Antonio yesterday, there are probably more than 1,000 two-dimensional materials, so layered structures that are known that could be exfoliated into single layers. So the number of heterostructures is really, really large. And this means that in order to guide experiments, and in order to find rational ways of designing heterostructures with just the properties we would like, as Feynman envisioned, we need obviously theoretical methods that can guide the search. Okay, and so that's the motivation for what I'll be talking about in the next 45 minutes. So here's an outline. First part of the talk, I'll be, so this is a more traditional kind of talk where I'll be describing how we compute electronic excitations. And this has three main parts. One of them is screening. So in order to be able to calculate excitations, we need to understand how electrons interact with each other. So we have to understand how screening works in two-dimensional materials and heterostructures. So then I'll talk about band structure engineering. So how can we tune the band structure of a two-dimensional material by exploiting the screening, okay, by engineering the dielectric environment of the material. I'll talk about excitons. And then the last part is on a database that we've been developing. So we've actually spent essentially all of last year, the entire group has been working on that single project. You could say it becomes a bit boring because we are carrying out more or less standard calculations, but we're carrying out very many of those in a very systematic way. And I hope this will eventually lead to something useful for the community. So that'll be the last part of the talk. Okay, so the code we're using at DTU, at the physics department, is GPOR. It's based on the project augmented wave method. And it's free under a GPL license. You can download it and use it. It's open source. It has a number of functionalities. One thing that I like a lot is the fact that there are three different basis sets in this code. So there is a real space grid, which is very useful if you want to do large calculations because you can parallelize over domains in real space. Then it has a plane wave basis set, and then it has an atomic orbital basis set, which is very efficient. And the nice feature is that at any point of a calculation, you can essentially switch between basis sets. So for example, if you want to relax a structure, you start with the atomic orbital basis, you relax very quickly, but not with very high accuracy because atomic orbitals are not as accurate as plane waves. And then just to get the last notch in the relaxation, you switch to the plane wave basis sets and continue the relaxation. Okay, so what I'll be talking about today is mainly using the many-body perturbation theory implementation. That is the RPA, the GW, and the Bethe-Salpeter equation implementations, which is all done in the plane wave mode, plane wave basis set. Okay, so there are three elementary types of electronic excitations in solid-state physics. There are quasi-particles. So that is basically a single electron together with its screening cloud, or a single hole together with the screening cloud. And these quasi-particles, they make up the band structure. Okay, they can be probed in transport measurements or in photo emission, for example. Then we have excitons. These are bound electron hole pairs, and due to the Coulomb interaction between the electron and the hole, this will lead to bound electron hole complexes that are sitting below the band gap of the material. And they are probed in optical experiments. Finally, we have plasmons. I won't be talking much about plasmons today, but these are collective excitations or collective oscillations of the electron gas, quantized oscillations of the electron gas in a method. So together, these three types of excitations, they determine the optical properties of the material. So understanding these types of excitations is really key to begin to design materials with prescribed optoelectronic properties. Okay, so let's talk about screening. So if we consider two charges in a two-dimensional material, then as you can see here, most of the field line will actually take place outside of the material, and this means that screening is going to be very weak in these materials. This is well known. There is another interesting aspect of this, which is that the fraction of field lines that are inside the material depends on the distance between the materials. So when the particles are close to each other, a relatively large amount of the field lines are inside the material, whereas for longer distances, a relatively larger amount of the field lines are outside the material. This means that screening cannot simply be described by a scalar dielectric constant as we're used to in Paul. So we get a non-trivial and non-local kind of screening in these materials. And this has some profound consequences that I'll come back to. So what does this mean mathematically? If we calculate the dielectric function, the static dielectric function of a two-dimensional material, this is what it looks like. This is the green curve down here. It's a function of in-plane wave vector. This is for hexagonal boron nitride. And the result for the layered bulk material is the black dashed line. And as you can see, for Q vectors that are large compared to the thickness of the two-dimensional material, the two curves, the curve for the bulk and for the monolayer, sort of approach each other. Okay, this means that for small wavelengths compared to the thickness of the material, screening is bulk-like. Whereas if we go to the opposite limit, in the long wavelength limit, where the wavelength of the field is larger than the thickness, then there is a very strong deviation between the dielectric properties of the monolayer and the bulk. So this means that when we talk about screening in two-dimensional materials, or in one-dimensional, or in reduced dimensional materials, then screening is wave vector dependent. Okay? So for long wavelength, screening is 2D-like, and it can be approximated by a linear dielectric function up here, 1 plus alpha times Q, where alpha is the polarizability. Okay, whereas for larger wave vectors, we go towards a 3D regime for the screening. Okay, now if we consider now a two-dimensional material embedded in a van der Waals heterostructure, or a two-dimensional material sitting on a substrate, then clearly the field lines here will be probing the exterior, the environment of the two-dimensional material. This makes it problematic, challenging to perform calculations, but it also shows that there is some opportunity there, because we can actually tune the way electrons in the two-dimensional material interact by changing the external environment of the two-dimensional material. So we have a knob with which we can actually affect the effective interaction of electrons in the material. Now, there is a challenge here, because typically these two-dimensional materials are not commensurate. So the lattice constants of different two-dimensional crystals will differ, which means that if we just stack two materials, we will get something that looks complicated. We have Moiré patterns in general. And this means we cannot just set up this entire calculation in a supercell. That supercell would have to be enormous to represent the system. So there is a challenge there, technical challenge. And the way we overcome that in order to describe the screening is that we've developed this quantum electrostatic heterostructure model, the QEH model. So we start with what we call the dielectric building blocks, which are a low-dimensional representation of the dielectric function of the monolayer here. So it's represented by its monopole and its dipole component. So with this minimal basis for describing the screening of the monolayer, we can now couple together all the different layers here electrostatically. So we're just solving basically electrostatic equations to couple these layers once we have the dielectric building blocks of each of the layers. Okay, so we are neglecting in this approximation the hybridization between the layers, but that turns out to be a very, very good approximation, as you can see here. So in this case, we're looking at plasmons and these types of heterostructures where we have the doped graphene layer and the doped graphene layer, and then we have some spaces in between hexagonal boron nitride that separates the two graphene layers. And what we find is we have a symmetric plasmon and we have an antisymmetric plasmon, because the two plasmons, they talk to each other due to the long-range Coulomb interaction. And this is the plasmon dispersion of the two types of plasmons here, the even and the odd plasmon. And all the points are full-fledged ab initio calculation for this heterostructure, and the full lines is what we get with the model. So you can see there is a perfect agreement. In the other plot over here, we fix the Q vector, and then we calculate the plasmon energy as a function of the number of hexagonal boron nitride layers in between. And we can only do the full ab initio calculation for up to 3 layers of HBN, but with the QEH model, we can continue that up to hundreds of layers if we like. So we can see how the plasmons will develop as a function of the number of HBN layers. Okay, so let me now turn to quasi-particle band structures. So here is an experiment where we shoot in a photon and we eject an electron, and then we can find the kinetic energy of this photo-ejected electron up here, the kinetic energy, and this gives us the energy of the hole left behind. This constitutes the band structure. And there is a very important thing here. So if we think, what is now the energy of the valence band? This would be the energy cost of taking an electron out. Okay, so once we take an electron out, we are leaving the system in a state that has one electron less than the neutral state. So it's now a charged system. And this is going to be very important because this charged electron, or this hole, will of course polarize its environment. So if this is a bulk material, okay, then we can imagine a photon comes in, shoots out an electron, now we have a hole, right? And that hole, after some femtoseconds, will be screened by the electrons in the system, and this will form the quasi-particle. So the energy of the quasi-particle is what matters. But if we have a two-dimensional material, then of course the hole will be screened by the electrons in the two-dimensional material, but it will also be screened by electrons that are sitting outside the two-dimensional material because of the long-range Coulomb attraction. And this gives us a possibility for tuning the band structure by the dielectric environment. So the way we calculate the quasi-particle energies is by solving the quasi-particle equation, which is the non-interacting part of the Hamiltonian, the Hartree potential, and then this exchange correlation self-energy. In DFT, we approximate this by a local exchange correlation potential, but the problem with this approach is that it does not capture the formation of the quasi-particle. So the screening here, which is essential in order to get good quasi-particle energies, is not correctly captured by these mean field approaches like DFT. So we have to do something better, and what we're doing, the gold standard for doing this is the GW approximation, where you can see that the screened electron-electron potential here, W, enters explicitly in the expression for the self-energy. Okay, so just a technical issue that you have to be aware if you're performing GW calculations for two-dimensional material. This is concerns the K-point convergence. Okay, turns out that the band gap of a two-dimensional material calculated with the GW approximation converges extremely slowly with the number of in-plane K-points. So you can see down here the green curve, which is just taking a standard GW code as it would be implemented and as it would work for three-dimensional materials, and then calculating the gap of MOS2 as a function of the K-point grid. And you can see the slow convergence here all the way up to 50 by 50 K-points. So we need something like 50 by 50 K-points to converge the band gap of MOS2. The reason for this is if you look at this expression here, what you have is an integral over the Brillouin zone of G times W. W as a function of Q involves the dielectric function as a function of Q. And we already looked at that, and you remember for small q, it's a linear function. So it varies strongly with Q, whereas in a three-dimensional bulk material, it's essentially constant as a function of Q, if you remember the plot for hexagonal boron nitride. This means that the region around Q equals to 0 has to be sampled on a very fine Q-point grid. And that's the reason for the slow convergence of the GW calculation. So what we did was we did this integration around Q equal to 0 analytically, because we actually know analytically the form of the dielectric constant around Q equal to 0. So we can calculate alpha easily, and then we have this and we can perform the integral around Q equal to 0 analytically. And this speeds up the calculations a lot, and you can see that the blue curve down here now shows the convergence of the quasi-particle gap with this new method. So we get converged around 10 by 10 with 10 by 10 K points. So this is an important point. So okay, here we did GW calculations for a range of TMDs. This is the band edges aligned relative to vacuum, and blue is LDA and red is GW. And you can see, this is just to show you that there is a large variation here. So it's very important to do the many-body method in this case. Let's pick one example, the well-known case of MOS2, just to see how GW performs. Okay, so these are the values from GW. The band gap is 2.5. That's actually an excellent agreement with experiments. But if we look at the absolute position of the band edges, we see that they are basically underestimated by half an eV by GW. So if we're interested in absolute band energies, we have to be very careful. because relative to experiments, they're not very good. What is actually missing in the GW is the vertex correction. Okay, so what the vertex correction does physically, it sits down here if you think in terms of Feynman diagrams. What it does physically is that once we create the hole, okay, think about the quasi-particle band structure, we shoot an electron out, we create a hole. This hole has a Coulomb potential associated with it, so it will polarize the material. Once it polarizes the material, it creates a change in the density of the host material. And then the hole interacts with the potential set up by that induced density. And that's the self-energy. Okay? If we do the RPA approximation down here, so neglecting the vertex, that induced potential is described in the Hartree approximation. And we know Hartree approximation is not too good for describing interactions in solid-state physics. What the vertex does is that it adds the exchange correlation contribution from the to the potential. Okay, so with the vertex correction, the hole interacts with the induced effective potential that it induces, which consists of the Hartree potential plus the change in the exchange correlation potential. Okay, and this has the effect of reducing the self-energy. Because the Hartree potential is too deep, right? Then it's increased a bit, or increased to some extent by the exchange correlation potential. That's the way it works. Okay, the Hartree and the exchange always have opposite signs. And what this means in practice is that all band energies are shifted up, in this case by roughly half an eV. So it's a significant change. Not in the gap, because the change is essentially the same for electrons and holes, for valence band and conduction band. Okay, so the gap is quite well described by GW, but the absolute energies are wrong. This is, by the way, also why the RPA approximation to the total energy has a systematic underestimation of the correlation energy. It's exactly the same reason. Okay, so let's get back to band gaps and screening. I'm showing you here a band structure of graphene on hexagonal boron nitride. There is an LDA and a GW calculation here. Just the black curves is LDA and the red is GW, and the gap of the HBN layer is here at the K point. So you can see, as usual, GW opens this gap. But what I'm interested in now is what happens as we change the distance between the graphene layer and the HBN layer. Okay? So if we imagine that so this could be a hole, or it could be an electron, depending on whether we are probing the valence band or the conduction band. Let's assume we are probing the conduction band. So we are putting an electron into the system, that into the HBN layer. That electron will polarize the graphene layer. Okay? And the electron will now interact with its screening cloud that is sitting, to some extent, in the graphene layer. So we can describe that as an image charge model. So we have a charge there, we have an image charge in the surface, which is now just a graphene layer. So we would expect that interaction, so the self-energy, the electron interacting with its induced image charge, to scale as 1 over the distance. That's exactly what we get if we perform a GW calculation. So here you can see a 1 over distance fit to the GW energies of the band gap of HBN as a function of the distance to graphene. What you can also see is that, so this is the asymptotic limit, this is the band gap of the freestanding HBN. So you can see the convergence here is 1 over distance, so it's very slow. If we do a standard DFT calculation, for example, the LDA, we don't see anything like that. So the band gap is converged at the equilibrium separation between the two. So that's what I already said, that these screening effects are not properly described using effective theories like DFT. Okay. If we do HSE or hybrids, other better approximations than the LDA, this curve here, the black curve, will shift up and get closer, but it will never show the 1 over distance dependence. Now, this was a case that was relatively simple to do with GW because the lattice constant of graphene and HBN is very similar. So we just set up a supercell. The in-plane size of the supercell is not going to be very large because we can just strain one material a little bit and fit it into a supercell. But in the general case, if we want to consider general van der Waals heterostructures, then the QEH model, we can use that to get the dielectric properties. But what about GW band structures? So if you consider a two-dimensional material now, which is layer I in a general van der Waals heterostructure, then we could write the energy of that layer as the energy calculated in a GW approximation for that isolated layer. We can get that and tabulate that. And then two corrections. One correction is due to the hybridization with the neighboring layers. And the other correction is due to the self-energy, so the screening that we would have to employ the GW approximation to compute. Now, this part can actually be treated at a DFT level. The hybridization is a single particle effect. We can treat that at DFT or even tight binding if we have a good parametrization. So that's relatively straightforward. The screening part is the difficult part because this requires many-body theory and the GW approximation. But what we are doing there is that we are describing this as the change in the screening. So we are assuming that the Green's function is not changed because the hybridization, after all, is going to be weak. So the Green's function is okay. But what is going to change is the screened interaction to W. And the change in W between having the isolated monolayer and having the monolayer embedded in the heterostructure, that we can calculate with the QEH model. So this now gives us what we call the G delta W method, which is a combined quantum mechanical many-body and classical electrostatic approach for calculating band structures of van der Waals heterostructures. And it actually works very well. So here we applied to the same system as before. The black dots were the full GW calculations, and the blue line here is what we get with this GW, or G delta W method. We've also applied it to a much more tricky system, which is bulk MOS2. So in bulk MOS2, there is, of course, a large amount of screening, but there is also a large amount of hybridization around the gamma point. Okay? And as I said, that hybridization can be described at the DFT level. So if we describe the change in the hybridization with DFT, and we describe the change in the screening with the G delta W method, then we get the blue curve over here, whereas the black dashed line is a full ab initio calculation for bulk MOS2. Okay, that's the black curve here. Whereas the blue is actually what we get for a monolayer of MOS2 sitting in a stack of 75 layers of MOS2. So we are using this, the QEH model, to capture the screening and the G delta W method to calculate the band structure, and then hybridization at the DFT level. So we can now describe with this method, I would say, any type of van der Waals heterostructure and the band structure in there. Okay, so I think I will just skip this example and move to excitons. So as I said already, an exciton is an electron-hole pair that is excited in a semiconductor, and the energy of the exciton is sitting here in the band gap. So they are essentially, if you want to describe the exciton wave function properly using quantum mechanics, you would have to solve the beta-salpeter equation, and this means that your exciton wave function, your many-body state, is a linear combination of electron-hole pairs. So it's a coherent superposition of electron-hole pairs across the Brillouin zone. If you now take the expansion coefficient f of k and you Fourier transform it to real space, you will find that that function of R satisfies a well-known equation here that looks like the Schrödinger equation for a hydrogen atom. This is called the Motte-Wannier model. Okay? So the f is nothing but the Fourier transform of the expansion coefficient of the wave function in reciprocal space. Okay? So this is a simple model for describing excitons in solid-state physics. The W that enters here for a three-dimensional system would just be 1 over r times epsilon. So it is really like a hydrogen atom with some screened interaction. For a two-dimensional material, W is more complicated because, as I've already said, the screening is not just 1 over r times epsilon, it's a more complicated function. But we can calculate that screening ab initio and plug it in here and solve the Motte-Wannier model. Okay, let's look at some real excitons. These are experiments on tungsten diselenide from Tony Hines. And what they measured here was the lowest 5 excitonic states in tungsten diselenide. So this is the Rydberg series here. This is the lowest lying excitons, the next, and so on.
Tungsten disulfide.
Tungsten disulfide, yes. I think you're right. Thank you. So it's a very nice experiment. That's probably also why you remember it. This is the band gap, and you can see first thing is that the binding energy of these excitons is pretty large. So the strongest bound excitons is 0.3 eV, which is really quite significant. And this is the two-dimensional material even on a substrate. So if you had this freestanding, it would be closer to 0.5 eV, right? But there's screening by the substrate that reduces it to 0.3. The interesting thing here is that if you take the standard 2D hydrogen model, you get this continuous curve here. Okay, so the excitons in this two-dimensional material cannot be described by the standard hydrogen model. Okay, so what we ask ourselves is, can we come up in this? So in this case, they basically fit it, and in order to fit these, you have to use a dielectric constant that depends on n. Okay, because the strongest bound exciton is very localized, so there you have to use a relatively large value for epsilon, because a large fraction of the field lines describing the interaction between the electron and the hole are inside the two-dimensional material, whereas for larger excitons, higher lying excitons with larger energy, the average distance between the electron and the hole is larger, and therefore a larger fraction of the field lines are outside the material, and therefore effectively screening is less. So you have to use a smaller value of epsilon if you're insisting on describing this excitonic series with a hydrogen-like model. So what we ask ourselves is, can we come up with this based on ab initio calculations? And so if we go back and we look at the hydrogen model here with a constant dielectric function up here, Q independent, this is nice because it has analytical solutions. But we don't know what to use for epsilon, because epsilon is in general Q dependent. So what we try to do, so this is epsilon, you can see it has a strong Q dependence, but for the relevant Q vectors here, we can actually approximate epsilon by a linear function of Q, as I've already said. And this means that we could try to define an effective dielectric constant for this exciton by averaging epsilon of Q over a region in reciprocal space that is roughly 1 over the radius of the exciton in real space. Okay? So that can then be done analytically if we use this expression for epsilon. And so then we get an effective dielectric constant because we have an analytical expression that relates the radius of the exciton to the dielectric function. Okay? So we have, so this is the energy and this is the radius up here. You can see epsilon enters there and there. This now becomes state dependent because the radius of the exciton depends on the quantum number in an L in the exciton series. But to make a longer story short, we can now obtain analytical expressions for the effective dielectric constant as a function of the effective mass and the polarizability of the material, alpha, the energy and the radius. And we can try to plot that analytical result versus an exact solution of the Montagnier Hamiltonian, so using the exact W of Q. Okay, and you can see there is a very nice agreement. This is for 50 different monolayered CMDs. We can, in the limit where alpha is reasonably large, the expression for the lowest bound exciton reduces to this expression. So the interesting thing here is that the effective mass drops out. This is very different from 3D, where the effective mass, where the exciton binding energy scales with the effective mass, but in two-dimensional material it actually drops out. And you can see this still gives a reasonably good approximation. Okay, so this, with this example here, this was fitted to the experiment. What we can do now is we can calculate this ab initio, and you see that there is a very good agreement with the fitted values. Okay, just to stress the effect of the substrate. In the experiments, they use silicon oxide as a substrate. With the QEH model, we can only treat layered structures, but it turns out that hexagonal boron nitride has a dielectric constant that is very similar to silicon oxide. So if we put the tungsten disulfide on a substrate of HBN, we can include the effect of the screening from the substrate using the QEH model. And then we get, you can see here, the blue curve, which is very close to the experimental values. The green curve over here is what we get if we consider if we calculate the excitons of freestanding tungsten disulfide. And the dashed line is the standard hydrogen model. Okay. So let me now talk about quickly interlayer excitons and van der Waals heterostructures. So far I talked about excitons in monolayers. But what is really exciting here is, of course, that we can stack different monolayers and get heterostructures. And if we consider just a bilayer, there are essentially three types of excitons. There is an infralayer type. There is a charge transfer-like type, where the electron and the hole are sitting in different layers. And then there is mixed types, where the exciton is a superposition of an infralayer and then charge transfer-like exciton. So this shows already that describing excitons in van der Waals heterostructures is a rich field. You can have many different types of electron-hole complexes that live in these materials. This is, of course, also what makes it exciting, because we have the possibility of really tuning the properties of these bound electron-hole pairs by changing the material. So here is a recent nanoletter where the authors looked at excitons in a trilayer consisting of MOS2, tungsten S2, and molybdenum MOSE2. Okay, so this is a TMD trilayer structure, and this is the band alignment they find based on DFT calculations. And what they find, this is the photoluminescence spectrum. So they pump the material here with a laser that is tuned to the band gap of MOSE2. So they create an infralayer exciton, and what they find is that the photoluminescence spectrum has a peak that is below the photoluminescence peaks of each of the individual monolayers. So this shows that there is an excitation in this trilayer that has a lower energy, and that must be an interlayer exciton. And what they, the way they interpret the experiments here is that this electron coherently moves to MOS2, and from there it recombines somehow, despite the large separation between the electron and the hole, but this is not really commented on in the paper. But they recombine and send out the photon with this energy over here. I think these materials here are really they're very challenging, but it's also an opportunity for calculations, because they are really ideal systems for benchmarking our electronic structure codes. We have here a system where, with atomic precision, we can change the interface, and we get atomically smooth interfaces. So it's very, very well defined at the crystal structure level. So these are really the best types of materials I can think of that we can use to benchmark our codes. So we tried to look at this system, and here I'm showing you a pretty busy plot. This is basically what we find if we use the Motte-Wannier model that I just described to describe the exciton binding energy, and then we add that on top of band structure calculations for the three layers performed either at the PDE level, the HSE level, or the GW with vertex that I talked about before. And what you can see is, so this is the results of the experiments, the intralayer excitons in the three layers up here, 1.9, 2.02, 1.57, and then the interlayer exciton between the MOS2 and the MOSE2 here at 1.5. And you can see that progressively, as we go from DFT, which has a way too low band gap, we go towards the GW plus vertex, we get an increasingly better agreement. And over here, at the highest level of theory, where we do GW plus the vertex, we get an excellent description of the infralayer excitations here, and also the interlayer exciton is only 0.2 eV off. So I think 0.2, perhaps 0.1 is the best we can hope for, given all the approximations that we are making. That is numerical approximations, but also approximations of the physical kind. So I think this is really a very nice result to show that these relatively complex excitations can be predicted with an accuracy of, say, 0.2 eV or less than 0.2 eV without initial calculations. Okay, so now just to summarize part one, and then I think I have 10 minutes, right? 6 minutes, okay, for the database, but I'll make it. So just a summary here: two-dimensional materials, fascinating playground for exploring and controlling electronic excitations. I think also a unique opportunity for method developers to test their codes against very well-defined experimental systems. The QEH model, I think, is really neat because it allows us to calculate dielectric properties of general incommensurable van der Waals heterostructures with hundreds of layers. And we can utilize that together with GW band structure calculations and DFT approximations to describe the hybridization to actually have a predictive modeling of band alignment, again in general van der Waals heterostructures. And then finally I talked about the screened hydrogen model, which provides simple analytical expressions for the different excitonic states in two-dimensional materials. So if you're interested in what I've been discussing here, it's all summarized in this topical review in 2D materials that came out late last year. Okay, so now let me switch gears and talk about this computational database that, as I said, we've been developing. It's been an immense amount of human and computational resources that we've spent in creating this database, so I really hope that it's going to be useful. So let me just say what it is. So as of today, this is continuously evolving, but as of today, it has structural, thermodynamic, elastic and electronic, magnetic and optical properties of more than 1,500 2D materials, calculated using state-of-the-art DFT and many-body methods. It has, so these 1,500 materials are distributed over 20 different crystal structures. So why would we like to spend so much resources on creating such a database? I think there are many, many reasons for doing this. First of all, not first of all, but first, it provides an easy, accessible lookup table if you're interested in basic properties of 2D materials. It reduces duplication of efforts. I don't know how many times in my group we've calculated the band structure of MOS2. So now we have, we've done that once and we don't have to do it again. It's in the database. We exploit actually computational resources much better because every time you do a DFT calculation, you're actually calculating a lot of stuff that you're not using. So suppose you're interested in a band gap, right? Then you calculate the band gap, but there is a lot of, you could also have extracted the effective mass of the charge barriers, the deformation potential, and so on. There's a lot of information that you typically don't extract. But by doing this, we are making sure that we're extracting all the possible information when we do the calculations, and then we're storing them and organizing them. It facilitates open sharing and benchmarking. I think it also enhances reproducibility of the data we make because it's very open. We also provide all the details of the calculations we do. It underpins method development. And then most importantly, I think this is a platform for accelerated materials discovery. And it's also a stepping stone towards designing van der Waals heterostructures with tailored properties. Okay, so the crystal structures we have, we start from experimentally known crystal structure prototype. Then we do combinatorial lattice decoration of this lattice. This yields a number of what I would call hypothetical 2D materials because they are not necessarily experimentally known. But we take each of these materials and we run them through a well-defined workflow that I'll describe on the next slide. And then we store all the data in the database. So here's the workflow. It's a bit complicated, so I'm not going to go through all the details, but basically over here, we relax the structure and calculate thermodynamic properties, so that's the basic characterization. One thing that we test for is dynamical stability, so is this structure metastable, or is it going to perform local distortions if you allow it to break symmetries or enlarge the supercell? If that's the case, we discard the material. We don't want to study it anymore, but if it's dynamically stable, so if it represents a metastable structure, then we continue and we calculate all the properties as shown over here. So these are the structures that we have. These are the 18 different crystal structures that we have in the database right now. So this includes a lot of well-known candidates. So these are the hexenes. These are the 3,5 semiconductors. These are the hexanes. MOS2 over here. We also have MOS2, where is it? Here in the T prime phase, because this is in the well-known 2H structure, but if you take it to the T phase, you know, it's not dynamically stable in the T phase. It actually wants to perform a structural distortion and lower the symmetry, and that's called the T prime phase, and that one we also have down here. Okay. We have Janus structures, somewhere up here, where we have sulfur and selenide and other types. We have MXenes, and we have organic, inorganic perovskites. So there is a lot of different types of two-dimensional materials here. This is what you see if you go into the database and you look for the band structure of tungsten diselenite. You will get a band structure like this. This is one of the things we calculate. And the color of the bands is the expectation value of the SZ component of the spin, so the out-of-plane spin component. So you can look at spin-orbit coupling. You can look at the position of the band extrema in the Brillouin zone. And if this is a metal you're looking at, for example, niobium diselenite, you get the Fermi surface over here, also with projection onto the different spin directions. We also provide GW band structures and HSE band structures with spin-orbit coupling, so you can see that as well. And here is, just to ensure you that things are done properly, this is an example of a BSE spectrum from the database for MOS2. Yeah, I'll just, 1 minute. This is an example of an absorption spectrum of MOS2. You see the A and the B excitons down here. And actually, if you look at the energy of the A exciton, it's according to measurements, it's 1.9. According to the BSE calculations we have here, it's 1.9. The quasi-particle band gap that we get from GW is the dashed line up here, which is 2.5 in the calculation, and it's also 2.5 according to photocurrent measurements. So this is where the RPA spectrum takes off. And these BSE calculations are performed with 48 by 48 K-point grid, which again is necessary to convert the spectrum to within 0.1 eV. So you can see here, this is an extrapolation of the exciton binding energy. And you can see it's actually not even completely converged at 48 by 48, but the error we make is less than 0.1 eV. Okay. Right, so we have 200 GW calculations and 200 GW BSE calculations for now. In the database we have 1,500 materials, but we don't have GW and BSE for all of them, of course, only for the smaller structures. But things you can do once you have this data is, for example, you can try to correlate the GW band gap with the PB band gap, and you see this, this nice correlation here. It's almost linear. You can also try to plot the binding energy of the lowest exciton for the semiconductors as a function of the Feng-Chuan direct gap, and you see that there is sort of a correlation, which you would expect, because if you have a material with a larger band gap, then screening will be smaller, okay? And therefore the electron-hole interaction will be stronger, and you should get a larger exciton binding energy, which is also what you see here. So these kinds of correlations are you can explore using the database. So the database is going to be online in a couple of weeks, and there's going to be a paper that describes the entire workflow and how things are calculated. So you can download the entire database, or you can browse it online. These data, or at least part of it, will also be uploaded to the Nomad repository. For those of you who heard about that, that's a big European project. A big repository where anybody can upload their DFT data. Okay, so with that, I would just like to thank the people who did the work, and not the people, but the organizations and the departments who sponsored the work. And thank you for your attention.
Oh, any questions or comments? Yes?
I have a question. So you show the Dirac function for 2D material, which is a function of an in-plane wave vector Q. But if we look at the static structure, multi-layer structure, so suppose we have the coordinates out of plane Z, for example, and so one expect that Dirac function as a function of Z or ZZ.
Yes.
And so I'm curious about we consider the interlayer interaction. So how do we consider screening?
In the QEH model, specifically, yeah, I can take that as an example. So we had this model that we used to describe the dielectric properties of the heterostructures. So where is it? One of the first slides. Here. So you can see that the set dependence of the dielectric function is described by these functions here. So the blue curve is the induced density in the layer if we apply an external potential that has an in-plane plane wave with a given Q and is constant across the layer. Then we are inducing this density, which is the blue line. So we calculate that and we store it on a one-dimensional grid, and we solve the one-dimensional Poisson equation to get the potential that induced density produces. We also calculate the induced density due to an externally applied field that is, again, a plane wave in plane, but then has a slope across the layer. And this produces this dipole density, and again, we solve the Poisson equation to get the corresponding potential. And now this potential, so suppose you have a heterostructure and you come with a field, so you induce these types of densities in all the layers, and they produce potentials, and those potentials introduce charges in the other layers that can be described across the layer as, and we do that either as a linear combination of constant and a slope, so first order approximation. And then we couple all this by solving a Dyson equation.
Okay, one write down explicitly the actual function of z.
Yes, yes. And then we just use a basis, which is this one. That's our basis. Yes, please.
Yeah, this was a wonderful talk, very impressive. You said at one point that with your methodology you can essentially take care of all possible van der Waals interactions. So I'm wondering, so as you know, there are these different cases, like molecule asymptotically is 1/r⁶. If you have a molecule surface, it's a different behavior. If you have a metallic surface, insulating surface, again, different behavior. Do you really have all these cases?
So for describing this methodology describes the dielectric properties and the band structure. So we are not calculating the forces between the layers, if that's what you're referring to. So we have to use EFT.
That ultimately determines the geometry.
This is going to be very important, yes, but that's going to be that'll be an input to this model. So once the distance between the layers is known, we can go on and compute the electronic structure. But you're right. I mean, we cannot relax the structure with this method.
On the substrate screen effect, right? So you do one calculation with increase the thickness of substrate and to see when the substrate screen effect could be. I mean, it looks like, could you go back to that big? Looks like after 3-layer substrate is used, the screen effect. But the result show it has been converged to the somewhere substrate effect on the band gap, right, or something like that. After put 3 layers of substrate, so the result has been converged. Right?
This one?
No, there is a curve. You compare different calculating result with the thickness of substrate, 1, 2, 3 layers. After put 3-layer substrate, so the result.
Did I do that? Okay.
Yeah. Let's see.
Interesting.
Yes. The binding energy around 3 layers, the difference has been very small, right?
So I mean, here this is not as a function of layers.
This A. What is A?
A. What do you mean?
Right figure.
This one?
Yes. A.
Oh, these are the different exciton series.
Yes. So what is different? If you really look at the dependence of this and this result with the thickness of substrate.
Okay.
So
yeah. I mean, I didn't show it here, but it's true that it actually converges relatively quickly with the substrate.
So you get how many layers?
I mean, of course it depends, but because if you have the electron-hole interaction depends on Q if you go to reciprocal space, and the small Q values will have components that go way down here, so that the potentials fall off as an exponential minus Q times Z. So for small Q, this is going to be long-ranged. But I think just, 3, 4 layers, I think is okay to get the main effect.
Okay, that's one. The second question is, if you really Well, you're using supercell calculation, right?
Not for this one, not for this one. This is the QEH model. So actually these calculations were done with 50 layers of HBM, just because...
So when you do the GW convergence test, so you're using supercell?
Yes.
So will the convergence of the GW calculation depend on the vacuum distance?
Yes, if you don't use a truncated Coulomb interaction, it will. But we're using a truncated Coulomb interaction. That means we have a 1 over r that is truncated in the z direction, right? So it's a step function. So this means electrons in 2 repeated layers, periodically repeated layers, will not interact with each other. Whereas in the in-plane direction, it's a 1 over r. So but this is a very important, I didn't mention it, but this is very important. And this is actually the reason why you see this very slow convergence of the band gap with respect to K points. Because I'm reading many papers in the literature where people are doing GW calculations not using a truncated Coulomb interaction. And in this case, they find that the quasi-particle gap converges very quickly with the number of K points. And that's also true, but it converges to the wrong result, because it converges to the band gap of a superstructure of layers with some vacuum in between. So this is essentially a 3D material where the dielectric constant does approach a final value for Q going to 0. If you use now a truncated Coulomb interaction, then you're describing a physically isolated layer, but the cost you have to pay is that now you have a dielectric function that goes linearly for small q, and therefore the GW band gap will converge slowly with respect to the K point. And that's where this analytical model for describing the dielectric function around q equal to 0 is important.
There are some STM studies which suggest that in layered systems, like especially topological insulators, the dielectric response at the surface is different from bulk, especially due to the presence of these topological surface states.
Yes.
Depending on where the Fermi level is located in the gap, the dielectric response can be different quite dramatically at the surface compared to the bulk.
Yes.
Do you have any suggestion or trick to somehow model this dielectric response using ab initio calculation, especially Bloom methods?
Well, I guess if you have a large enough computer, you can just calculate the dielectric function. But I guess that's the problem, that you want to have a simple way of doing it. Because I think if you have a topological insulator, you have a metallic surface state.
Yeah, exactly.
And then you calculate the susceptibility chi. Of course, it will be a function of z and z prime, where z is the distance perpendicular to the layers. And obviously, when z and z prime are close to the surface, you will have a large dielectric response. But as you go towards the bulk, you will get a dielectric kind of response. So you have to find a way of dealing with this z prime dependence. But then I think one could do something. Yeah, but I didn't think about it explicitly.
Thanks.
Yes.
So, in your calculation of quasi-particle band gap, that is still an isolated one for MOS2, right? At the end, you see quasi-particle band gap is 2.5, X-term is 1.9. This quasi-particle band gap kind of slowly creeping down compared to things done about 4 or 5 years ago. So what's
yeah.
And as the experiment, it's sort of very interesting at the beginning. All experiments
so exciton binding energies were 1 eV to begin with.
And then all the experiment shows very large band gap, and then later on more and more experiment shows smaller than the calculation.
That's true.
Slowly.
I think, if you look at our calculations, we haven't been that inconsistent.
Okay.
We've probably stated band gaps of MOS2 of 2.65, and now we're saying 2.5. Of course, mid-orbit effects have something to say. That closes the gap by 0.1. In-plane lattice constant is another thing. But I think K-point convergence is the main thing, right? But it's a good observation. I think we're converged now.
Okay.
Okay, we have one more question, please.
Yes. Very impressive. I have a simple practical question. Near the end of your talk, you show an example of, I don't know which material. So my question is, what kind of computing facility you use to do the calculating and how long it takes? The
PSE calculation with 48 by 48?
Yeah.
Yes. So we use here a plane wave cutoff for the local field effects, the G and G prime vectors of 100 dB, if I'm not mistaken, or 80. And then we included 4 conduction band and 4 valence bands. And this takes around a day on probably something like 100 cores.
Oh, only one day, not a month?
No. I mean, then.
That's very.
But this is a small system, right? This was a MOS2, 3 atoms in the unit cell. As soon as you go through.
4 bands may not be enough.
I think it's enough for this system. But you know, it depends on systems. You have to look at the band structure to figure out which group of bands to include.
Okay, so I have one minor question. Yeah. Okay, so you mentioned you have the vertex. You deal with the vertex. So that means your GPOWs or any packages you use, you can really do the fully self-consistent GW and not just beyond the GWA.
This is not self-consistent GW. This is non-self-consistent G naught W naught.
Yes.
Starting from PDE typically.
Yes.
But we include the vertex.
Yeah, but if you really just go through whole together,
yes,
you can really approach the the fully self-consistent GW.
We can. Yes. And we have tried that. I mean, updating the eigenvalues only. Yes. That's pretty robust. That works. You can get energies out.
How about the green function? How about green function?
The green function, the student didn't succeed. But we had a project trying to do this quasi-particle self-consistent implementation. But it's not there in G4 for now.
Thank you. Okay, thanks to Professor Thygesen again. Okay, the next speaker is Professor Lin Fa from